All right, hi guys, welcome back to part two of Basic Chem and Water Properties notes. This section is just about water and its properties and why it's cool and how it's for its life. So we're going to talk about that a little bit. It's definitely a continuation from what we just talked about in chemical bonding. So first of all, water's shape actually is what allows for hydrogen bonding as well as its polar covalent situation. So it's not just because it has a covalent bond, it's because it has a polar covalent bond, and also because its shape is really conducive to hydrogen bonds forming. So the overall charge, as we talked about in the last video, is unevenly distributed. So even though an entire water molecule is neutral, within that neutral molecule, there's the oxygen that has a little bit of a negative going on and the hydrogens that have a little bit of a positive going on, which gives water this like sort of sticky ability, which is really cool. So here's some water in this picture. Again, remember the dotted lines are the hydrogen bonds. So these guys are hydrogen bonds. And the lines, the solid lines when you can see them, are covalent bonds. And in this case, they're polar covalent bonds. Here's another joke about polar things dissolving. So there's a polar bear and he's like, I'm dissolving. And it's because he's polar, and polar things and ionic things will dissolve in water, whereas non-polar things will not. So there you go. All right, water properties. This is probably going to be a little flashback back to freshman bio, if you can remember it. So water has two properties, cohesion and adhesion, that kind of go together. Cohesion is water's ability to stick to other water. So water sticks to other water molecules. And this is done using hydrogen bonds. Cohesion is what gives water its really awesome surface tension abilities. We'll say leads to great surface tension, which is the reason that like water bugs can walk on water. And if you like fill a glass all the way to the brim and then look at eye level with it, you'll be able to see like the bubble kind of forming over the top. And that's because those water molecules are hydrogen bonding to one another, and that's strong enough to keep them together, to keep them from like overflowing. And then adhesion is water sticks to other substances. And these substances have to, of course, be like attractive to water. So they have to be polar or charged. So an example of this is when you're measuring, and you guys know you have to measure like with the meniscus. And the reason you have to do that is because the water is adhering to the sides of the graduated cylinder or whatever, test tube, whatever you're measuring. Adhesion is also really important for water being able to move up the trunks of trees and the stems of plants. I'll show you that in a few minutes as well. The capillary action concept is related to both adhesion and cohesion, where you can like put your finger over the top of a straw and suck some water up into it. Is kind of like capillary. That is capillary action, which you can test. Okay, so along with that, water is a super versatile biological solvent, which means that it's able to break down and separate different substances that are put into the water. Of course, this is like not always true. It's not true for oils, but it is true for salts and sugars. Anything that you would dissolve in water if you were cooking, you're able to do that because water is this biological solvent. Another cool thing about water that you have witnessed, I'm sure, is that it expands when it freezes. That's because of the way the hydrogen bonds form in this tetrahedral arrangement. You can Google a picture of this super easily. I should have put one on here, but it's easy to Google. And because of that, because of the way that it hydrogen bonds, there's more airspace in between the water molecules. So that makes ice a lot less dense than actual liquid water, which is why ice floats on the top of the water. Um, the hydrogen bonds in ice, every water molecule is hydrogen bonded to other water molecules. But in liquid water, it's breaking all the time. In water as a vapor, there's very little hydrogen bonding because the molecules are so far spread apart and they're moving so fast. There is still occasional hydrogen bonding between the molecules, just not as much as there would be in the liquid, and definitely not as much as there is in ice. So, okay. Here's just another little cartoon about water breaking down, being that biological solvent. So that's what this is about. Biological. So it's able to take these, this is sodium chloride, a salt. It's able to take the salt and attach to it using its partial positives and partial negatives and kind of pry those atoms apart. That's what that means. And this is an image that kind of shows it. Okay, so here's a image that shows a tree using adhesion to get the water up to the top of the tree. You might already know this, but plants do not absorb any water from their leaves. They actually lose water from their leaves. So all the water in a plant actually came from the roots, which means that they have to work against gravity to get their water source all the way up to the top. Even if it's a small tree or a small plant, working against gravity like that is not super easy. But because of water's properties, it's able to work and it's able to happen. So this is just one small way that water's properties sort of allow for life on Earth with cohesion and adhesion. And you might remember too, this is just kind of a throwback fact, but water is moving through the xylem of the plant, and then sugar is moving down through the phloem. So xylem, phloem, freshman bio flashback. Okay, here's here's a picture of the ice. Good, I'm glad that's on here. But so this just shows the difference in hydrogen bonding with ice and with liquid water. And this is the reason why the ice is floating up on the top. But you can see there's just so much more airspace in the ice picture because of the way the hydrogen bonds have formed. And in liquid water, the hydrogen bonds are a little more random. They're also constantly breaking and reforming. And so that's kind of the difference. But that just allows the ice to float up on the top, and also the water underneath then doesn't freeze and allows like life to continue. All right. So now let's talk about water and heat and its like really cool abilities related to that. So just sort of a refresher to from physics, or maybe you didn't know, but heat is just a measure of the kinetic energy of the molecules in a substance, and that's actually what temperature is a way to measure that energy, the movement of the molecules. Like every type of energy, and this is going to be important when we talk about like enzymes and even when we talk about diffusion and osmosis, that things are always trying to move from a high concentrated area to a lower concentrated area. So when we talk about that in relation to heat and low, so the heat is trying to move to an area where there's less heat. I mean, I'm saying heat, but I mean like the energy that is causing the heat to happen. So just kind of a cool fact related to this is that ice is actually absorbing the heat from the drink. It's not giving off cold because the heat is trying to, the energy that is creating the heat is trying to move to where there's less energy, and where there's less energy is in the ice. So we always say like the ice cools your drink, but really it's like sucking the heat out of it. Um, and along with that, over here, cold is not really a thing that like exists. It's just the removal of heat or the absence of heat, um, which is just kind of a cool concept if you haven't really put it that way in your mind. All right. So now water has high specific heat and high heat of vaporization. And these are things that are actually really super important to its helpfulness for living things. Specific heat is the amount of energy it takes to raise the temperature of 1 gram of, in this case, water by 1 degree Celsius. So because water has a high specific heat, it means it takes a ton of energy to actually raise the temperature of water. This is something that you probably have witnessed if you have gone to the beach, either like early in the summer where it's a hot day outside, but the water's still really cold. Or if you've gone to the beach like pretty late in the fall, like in October, it's cold outside, but the water's still really warm. So that's just one example of how water is, it takes a long time for it to change in temperature because of its high specific heat. That's great for ocean animals. It's great for climate because if the temperature of water like shot up and down all the time, it would be really hard for ocean or even just other freshwater animals to maintain homeostasis and survive. It also would be like crazy time for the climate, which is obviously bad news whether you live in the ocean or if you live on land. So it's useful because it moderates climate and allows organisms to inhabit water. Also, it's really useful to you inside your body. So you I'm sure know this. Your body is mostly water, 70%. Males and females actually have a slightly different water breakdown. I think females are more watery, but I have to check on it. But think about if the temperature of all the water in your body could change really fast and didn't had a low specific heat, then it would be so hard for your body to stay functioning. If you like overheated, you would like boil from the inside. That would be totally dreadful. So the fact that water resists temperature change the way that it does um, is really a huge reason that life exists. Similarly, water has a high heat of vaporization, which means that the amount of energy that it has to absorb to turn 1 gram of liquid to gas is also very high compared to other substances. So what that means too is that when water evaporates, it's the hottest molecules that are leaving, which allows you to feel cooler when hot water molecules evaporate off your skin. And that's how one way that sweating actually cools you down. So it's useful because of sweating. A dog panting. And similarly, like with bodies of water and stuff, the hottest water molecules are actually going to leave. They're not going to stay in the water like circulating. So it allows the whole body of water to remain cooler. Okay, last thing that we're going to talk about in this video is pH, which is also related to water. So water dissociates, it breaks into a hydronium ion, which is H plus, and a hydroxide ion, which is OH negative. Your H plus ions are acidic, and your OH is basic. Because water has equal amounts of both of these things, water is neutral. Which you hopefully maybe remember that a neutral pH is a pH of 7. A low pH is going to be acidic, and a high pH is basic, or you can also call it alkaline. So if you drink those like fancy waters like Essentia or anything that says like alkaline water, it's supposed to be better for you. It's slightly basic. The closer you get to 7, the more neutral you're going to get. So an acid that has a pH of 6 is going to be like a pretty weak acid, whereas an acid that has a pH of 1 or 2 is going to be super, super strong. And then just another like misconception that happens sometimes related to pH is that a super strong acid and a super strong base are both going to be really poorly bad for you. I think people tend to feel like acids are scarier, but really strong bases are also scary. So the further you get from neutral, the more danger living things are going to experience. Okay. Buffers are substances that are able to keep pH neutral. So they're able to absorb H plus when it's in excess and then release it when the solution's becoming too basic. This is really, really important for blood pH and for us to be able to like maintain homeostasis. I'll put that on here. Super important for homeostasis. And just as a refresher too on that word homeostasis, that's maintaining a stable internal environment. Every cause of death at the end of the day is just irreversible loss of homeostasis or failure to maintain it. So it's super, super important, and buffers are a major way that we're able to keep our blood pH in check. Your blood pH, if it gets off even by 0.2, it can kill you. So it's really important to have these buffers working and doing what they're supposed to do. Here's the reaction, just kind of showing you water dissociating and reforming into a hydroxide and a hydronium. And last thing we have here is the pH scale, your old friend, just kind of showing you a few things that are on the scale. 7, of course, is neutral, and it also shows you like the H plus and OH ion breakdowns that are happening over on the left side. But you can see here that as you start at 0, you're super, super acidic. Then as you move down, you become more neutral, and then you become more basic. So like I was saying, like you have battery acid and like stomach acid up here where the strong acids are. Down here at the bottom, you have things like bleach and ammonia, which are, of course, not good for you either. So either way you go, not super great. Pretty amazing. Gastric juice is really, 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 really acidic. That's why people get ulcers, because the acid starts to like eat away at their stomach lining. And then you can also find like other body fluids on here too. Saliva and blood, tears, urine are all going to be pretty close to neutral, which is where you want them to be. So, all right, that's the end of this. Review of water properties, pH, and that's it. And I'll catch you guys next time. So if you have questions, feel free to ask me, send me a remind, ask me in class, send me an email, whatever you need to do. And I'll definitely get back to you. But thank you so much for watching. Thanks for working hard. You're the best. Have a great week.